Hey, we left up here on page 2. We finished it up, so we're going to go on to page 3. Page 3 is when we start actually graphing some stuff and talking about those graphs and the functions. And as you can see, there are 6 parts, technically 7, I believe. But to each question, I'm going to read them because you should always read the directions. It says to solve for the inverse, graph the original, which I'm going to highlight because this is the one where it says to graph the original and the inverse. So that is a two-parter. Determine if the inverse is a function, so that's just a yes/no. Determine the domain and range for both the original and the inverse, so once again, that's a twofer. And then find the zeros of the original and the inverse function. And find the domain restrictions of the inverse, if there are any. Sometimes there's not. And here we go. Maybe I'll talk about the full find the domain restrictions first. There are only 2 types of domain restrictions we're doing in this class. The first type is anytime you have an even root. So like if you have a square root or 4th root or 6th root, those will have a domain restriction. And the other thing is if we had fractions, like if you have a 1 over x, anything like that. Basically, there's an x on the bottom of a fraction, then there's a domain restriction. But those are the only 2. We have not done other ones. There are other ones, but we're not doing any right now. So like in this one right here, x squared minus 4, it does not have a root. It is not a fraction. There's no x in the bottom or anything, which means this is not going to have any domain restrictions. So I can automatically just put none. And if I look at the next problem, I see that this one does have a square root. Because it has a square root, there is going to be a domain restriction. So maybe I'll just like write myself a little note saying that there is going to be a domain restriction on this one. I'm not going to write just yes, because you do have to write what it is in interval notation. But there is going to be something here. Okay, so going back here, it has a bunch of information you need to do, but believe it or not, I don't actually do things necessarily in the order they ask for it. For instance, I don't solve for the inverse first. I go straight to the graphing, because if you have the graph, I'm sorry, I'll say it the other way. If you solve for the inverse and then you graph it, sometimes they don't actually match because of restricted domains. But if you graph the original and then graph the inverse like we did on the previous video, where you just switch the ordered pairs and regraph it, you're 100% going to get the right answer. So right here, x squared minus 4. I'll just double check to make sure what I'm doing is correct in the calculator because I'm paranoid. But we have covered what this is going to kind of look like. An x squared is called a quadratic. And a quadratic is a U-shape. It is a U-shape. It goes like that. So it is going to be a U-shape like so. And this is technically in vertex form. If you forgot what vertex form is, basically there's usually something in parentheses here that you would switch, but there's not here. So like the vertex is going to be at 0, -4. So 1, 2, 3, 4. And as I said, it is a U shape, so it's going to look like this. And because of reasons I'm not necessarily going to tell you right now, I know for a fact that I'm also going to have points here. There is a trick, and it's kind of cool. Basically, quadratics always go up by odd amounts. So it goes up 1, 3, 5. Ha ha ha. How do you know that? You don't have to. You can just press y equals and plus x squared minus 4. And if you press that, you can see, sure enough, that it looks like that. It's going to be a u going through those. Hold on. Boom. Boom. You can always press second graph, and it'll give you the ordered pairs, the ones that I just did. So, yeah, 1, 2, 3, 4, 5, 6, 7. Those 7 points you can fit on your graph. So those are the ones I graphed. 1, 2, 3, 4, 5, 6, 7. So graph them and you're good to go. But as I said before, if you want to graph the inverse, you can just take these ordered pairs and graph them, but in opposite order. So I can do 5, negative 3. So 1, 2, 3, 4, 5, negative 3. I can do 0, negative 2, which would be right there. Negative 3, negative 1. Negative 4, 0. Negative 3, 1. And then 0, 2. And 5, 3. So 5, 1, 2, 3. And what we talked about on the previous page, if you see a special point, like this is 0, negative 4, that means negative 4, 0 is going to be that same special thing. So since this is a turning point, this will also be a turning point. And from there, you can probably figure out that it's just going to be a U going out this way. And you should always double check that it does look like it reflects across this main diagonal. And it does. If you just do a kind of line like that, you can see that it is the same on the left and the right. So those are inverses, and we're good to go. I know for a fact that's the inverse. I don't even have to know what the equation is. To solve the equation, though, which is what we have to do there, what you do is instead of f of x, you write x, and instead of x, you write y. So you would get x equals y squared minus 4. You're switching the x and the y, just like you did with ordered pairs, but this time, f of x is the same thing as y. So you're switching the x and the y, so it's x equals y squared. And then you would solve for y. So in this case, I would add 4 to get x plus 4. And then to get y by itself, you would have to square root both sides. Just remember, when you square root both sides to get rid of the square, because you square rooted both sides, you have to put a plus or minus in front. So I would get y equals plus or minus the square root of x plus 4, which is what's going to go up here. Note that I did not write the y because it already has that part right here. The inverse is plus or minus x plus 4. So that plus or minus thing is kind of weird. It does match with the graph, though, because positive square root, if you forgot what a square root graph looks like, square root is a point, and then it goes off to the side like that, so it's like a point. This right here is the square root part of 4, like if you ignore this. This is the square root of x plus 4, but negative square root of x plus 4 would just flip it up like that. So this is the positive and negative versions put together, which is why that plus or minus is there. Is it a function? Well, it fails the vertical. Well, this one fails the vertical line test. This one fails the horizontal. So this is not going to be a function. The domain of the green one, the original, excuse me, it's going to be all real numbers. So I'm just going to write all real numbers. The range of it, though, it looks like it has the bottom at -4, and it goes up to infinity. Infinity is always a parenthesis, but since this is a solid point, this will be a bracket. So -4 to infinity is the range. Domain is -infinity to positive infinity. On the previous paper, we talked about how the domain of one is going to be the range of the other, and the range of one is the domain of the other. So I'm just going to go ahead and copy-paste this, save on time. But you can always verify just by looking at it that it's true. The domain is -4 to infinity, and the range is -infinity to positive infinity, so all real numbers. Okay. Zeros. Zeros are just the x-intercepts. So like, boom, boom. The original goes through -2 and 2. The inverse, the red one, goes through right here, which is -4. And that's it for the first one. The second one, I'm going to try to fit into this video. well, let me see. Yeah, try to fit into this video. I'm going to graph it. Square root of x minus 2. It's going to look like that. If I go to the table, bunch of errors, but I do see 2, 0. I see 3, 1. And then 6, 2. 1, 2, 3, 4, 5, 6, 2. So I can get 3 points on there, like so. And if I switch the points, I could do 0, 2. I could do 1, 3. And 2, 6. To look like that. And that's the inverse and the original. Make this a y. So instead of y equals the square root of x, I would do x equals the square root of y minus 2. To get y by itself, you would square both sides. You would then add 2. So then y would equal x squared plus 2. Now, if you graph x squared plus 2, it does not actually look like this. It turns out x squared plus 2 looks like this, an entire u. But as I said, we're going to have a domain restriction, which is why it's not going to be a u. It's just going to be half of a u. This does pass the vertical line test and horizontal, so already yes. The domain of the original, it looks like it starts, the farthest left it gets is 2. The farthest right it gets is infinity. For the range, the lowest it gets is 0. It goes up to infinity. And I can just flippy-floppy these. This will be 2 to infinity. This will be 0 to infinity. And I can just go straight to domain restriction. It's just going to be this. You know, the domain of the inverse is 0 to infinity, so the domain restriction is that it has to be 0 to infinity. Which you can also look at the graph. See, its domain is 0 to infinity. It had nothing on the left. It's just 0 to infinity is the domain restriction. The zeros, it looks like there's a 0 right here at 2. But if you look at the blue one, it doesn't have any, so I'm just going to write none. And that's it for that problem. I'll zoom out so you can get a full view of everything again. But that is everything on this page. Hopefully it makes sense. If not, feel free to, rewind and rewatch it again or go elsewhere. I don't know. Up to you. Have a good one.